Thank you, Chuck, and thank you. I want to thank the organizers as well for this opportunity to speak. So I will try. Okay, so the result that I want to talk about is the following. Let's call it Theorem 1. Okay, so let's formulate it as follows. The smooth affine Koros-Russell threefold. So let's this is something we can write up explicitly. So let's so for this talk, KR will be an abbreviation for Koros-Russell. It's not a T as real K theory. Here's the equation. It's x plus x alpha to the alpha 1 times y plus c to the alpha 3 plus t to the alpha 4. This is supposed to be 0 inside A4. And let's, for simplicity, just work over the complex numbers. So these alpha 2, alpha 3, yeah. Thank you. Checking you're awake. So these are integers, and we require that alpha I is greater or equal to 2, and alpha 2 and alpha 3 are relatively prime. And the statement is that this here is A1 contractible. And I should add that it's really the first such example of an A1 contractible variety different from an affine space. So it's the first such example which is not isomorphic to an affine space. So one should notice here maybe that, of course, these conditions on the exponents, the alpha i's here are quite important. So that if alpha 2 or alpha 3 equals 1, then this equation here just describes a A3. Okay? But because of this condition here, this ensures that the Koros-Russell threefold is not an A3. So this theorem here is a result of, well, it's the effort of quite a few people. So I want to mention Aravind Asak, who sort of initiated the study of this example in the context of A1 homotopy theory. Then there's a paper by Mark Oiva, Amalendra Krishna, and me from last year, who almost proved this result, but not quite, and then a paper by Duboulot, Facel, which will be published, I think, this year. Both of these papers have or will appear in algebraic geometry. Okay. All right, so I want to try to explain, or at least outline the proof of this here, and try to give you the context in which this theorem here sort of fits. And then if time allows, try to tell you where I think this example is really leading us. So let's start with some fun facts about the Koros-Russell threefold. So those threefolds, they have a long and rich history. And I want to mention the following results on them. So first off, there are so-called an exotic A3. So this means two things. So the first statement is that when we take Kr and look at its complex points, then we have and view the complex points as a real manifold, then then that manifold is really diffeomorphic to R6. So topologically, this is a Euclidean space, while algebraically, it is not an affine space. So concerning 1, so the way to prove 1 is to show that the complex points of Kr is a contractible manifold. So, so this here, if we can show that this here is contractible, and this was done by Kalimann and Seidenberg in a paper in 1999 using the technique of affine modifications. So once we have this, then it follows that we have this diffeomorphism. So the complex points are really diffeomorphic to R6. And this is a theorem of Dimkheim and Ramanujam.
Is the 1, is that real analytic or just diffeomorphic?
It's diffeomorphic as a...
Not real analytic.
No, just diffeomorphic as manifolds. Right. Right, and then point 2, this is actually quite a difficult result. This was achieved by Makalimonov in '96. The way this goes is to introduce the so-called Makalimonov invariant of Kr, which is defined as the intersection over all the actions of the affine line viewed as an algebraic group on Kr, and then we look at the coordinate ring of Kr, and we take the corresponding fixed points. Okay, so we're looking at all the possible GA actions on Kr, and take the intersections of the fixed points on the coordinate ring. And as Makalimonov proves, this here turns out to be a polynomial ring in the variable x. And this x here is really the x that appears in the definition of the Korras-Russell threefold. On the other hand, if we compute the Makalimonov invariant of any affine space, because we have translation actions of GA on affine spaces, this is just the complex numbers. Okay. So these two calculations combined tells us that Kr cannot be an A3. So, so if you want to see a little bit more of the geometry behind this, we can look at the projection from Kr, say pi x, down to the affine line, say in the variable x. Then, if you look at the fiber over 0 of this projection, then what have we? So over the closed point 0, what we have is the cylinder sort of on the cusp. So this is A1 cross the part of the equation that deals with C and T. So this is C alpha 2 plus T alpha 3 equals 0. So if you like, this looks a little bit like this here. Okay, so this is so-called the open book surface. I mean, if alpha 2 is 2 and alpha 3 is equal to 3, this is literally the book surface. And there's a criterion due to Kalimann from 2002 saying that if you have a map from A3 down to A2 with the property that the generic fiber is A2, then all the closed fibers are isomorphic. But if you look at other closed fibers here, for KR, that's just a copy of A2. So this also tells us, this is more like a geometric explanation why the Koraz-Russell threefold cannot be an A3. Okay. I'll try to use the squeegee. Okay, so there's another sort of reason why we're interested in these Koraz-Russell threefolds that I want to emphasize, and this has to do with the Zariski cancellation theorem. Okay, so another fact about KR is that it's a potential counterexample to Zariski cancellation. So a variant of this was formulated in 47 by Zariski. Let's state it as follows. So suppose X is a smooth affine complex variety. So, so if it happens that the cylinder on X, if this here is an affine space, then is X itself an affine space? So classically this holds for n less or equal to 2. Or D less or equal to 2. So I stated this for complex varieties. If we instead work with varieties of in positive characteristic, then Gupta has counterexamples in any dimension greater or equal to 3. That's quite recent, from 2013. Okay, so so this Zariski cancellation conjecture or problem, of course, this is closely related to A1 homotopy theory. So, let's just briefly try to recall what A1 homotopy theory, how it's constructed. So, a little bit about A1 homotopy theory. Okay, so a good starting point is the category of smooth schemes over the complex numbers. We put all of them inside one bag, and here the relevant objects for us today will be A1. A1 is, of course, the object we parameterize our homotopies over, and when we stabilize with respect to P1, and the other object that we're interested in, at least today, is the Koraz-Russell threefold. Now, since the beginning of time, we also had another category called simplicial sets. So here we have things such as simplices, ordinary spheres, but there are also things such as NURBS of categories in here. So this is really a rich category. And in A1 homotopy theory, we take these two categories and we put them into the same category. So this leads to motivic spaces. Motivic spaces A over C, defined as contravariant functors from smooth schemes over C into simplicial sets. And then there are functors in here from simplicial sets. Simplicial set can just be viewed as a constant motivic space, and here we have the Uneda embedding. So of course the thing that we're really interested in are smooth schemes, and we want to try to study them in terms by just putting them into the same category as simplicial sets. Okay. So the first thing one really needs to do is to put some model structures on motivic spaces. And the first model structure, say, is what I like to think of as a sort of a free model structure where the fibrations and the weak equivalences are defined pointwise. So there's a free model structure on motivic spaces over C, where the weak equivalences and the fibrations are defined pointwise or scheme-wise. We just, if you have such a motivic space, we just look at that. We just evaluate on any scheme and look at if we obtain a weak equivalence or a fibration in simplicial sets. Okay. So then next thing is to impose relations. And the experts will notice that I'm lying a little bit, just for expositional reasons. So the first relation is so-called varieties. So, so that's varieties for squares. Squares of the form that we take an open cover of X. So in reality, we are allowing more general squares, so-called Nisnevich squares, but this is basically the idea that we cover our our schemes by sub-schemes and then impose varieties for such squares. And this is so-called local model structure. And this is due to Choyal and Chardin. So in this local model structure, we haven't really changed much of the category of smooth schemes over C, in the sense that if you take the Uneda functor into motivic spaces and compose with a map down to the homotopy category with respect to this local model structure, then the composite is still fully faithful. So far we haven't really identified any schemes in the homotopy category yet. But that happens in the next step, where we impose A1 homotopy invariance. So this is due to Morel and Blavatsky. So in this case, well, we insist that the projection map from the cylinder on X down to X is a weak equivalence for all X in smooth schemes. Okay. Now, of course, this setup here relates directly to the Zariski cancellation theorem. So note, or the Zariski cancellation conjecture. So, so if it happens to be true that the Koraz-Russell threefold is a counterexample to Zariski cancellation, then necessarily it is A1 contractible. So if Kr, if the cylinder on Kr is an A4, well then Kr is A1 contractible. So it means that the map from X down to spec C is an A1 weak equivalence. Thank you. Okay. All right. So I want to talk next. I want to talk about a program due to a SOC. And the program is about how to prove that Kr is not A1 contractible. Okay, so it's sort of the opposite of theorem 1. So I want to explain, why that fails. Some sense it would have been more spectacular if it turned out that the Kr is not A1 contractible, but that's not true. Okay. So Asok had the following really ambitious program. So to show that Kr, let me write it like this, it's not A1 contractible. The idea is to find one A1 cohomology theory that detects non-triviality of Kr. And the idea here is to invoke the GM action on Kr. So there's a GM action. So GM, the multiplicative group, so that there's a GM action on Kr. So let's describe it as follows. So we take an element of GM and we want to act on a quadruple X, Y, Z, T. This is set to be equal to lambda to the alpha 2, alpha 3 times X, lambda to the minus alpha 2, no, alpha 1 minus 1 times alpha 2, alpha 3 times Y, and then lambda to the alpha 3 C and lambda to the alpha 4, alpha 2 T. Okay. Now, with respect to this action here, Asok proposed the following. So the first step in this program is to notice that, okay, if you fix a prime P, then mu P, the sheaf of groups of P's roots of unity contained in GM, also acts on Kr, and we can ask about the fixed points. And we want this here to be exactly the fixed points of the action of GM on Kr for almost all primes P. That's the first step. Second step says that so if we have a map F, say from X to Y, now we look in the smooth schemes over C equipped with a mu P action such that F, say F and the fixed points of F with respect to mu P, if these are both of these are A1 weak equivalences, well then, the induced map on K naught, so mu p equivariant K naught on F, this is an isomorphism. And then secondly, thirdly, and this is the last step, is to show that in mu p K naught, the map induced from just the structure map from Kr to spec C, this is not an isomorphism. For almost all P. Okay. All right. Okay, so so I claim that combined, those three steps tells us that Kr is not A1 contractible. So let me try to explain that. So first of all, the GM action on Kr, that has a unique fixed points. The only fixed point is the origin. So note here that Kr, this has a unique GM fixed point. Origin. So if you look at 1 and 2 and 3 combined, they imply that there exists a prime P such that the mu P fixed points of Kr, this is A1 contractible because it's just a point. And moreover, the K naught mu P of Kr, this is non-trivial. Non-trivial in the sense that it's not the mu P K naught of the complex numbers. So if Kr, so in addition, if Kr is actually A1 contractible, well then to here, this contradicts the non-triviality. Well, OK naught mu P, OKR. Okay. So this program was in the making for quite a few years, and the first results are as follows. So Philip Herman, in his PhD thesis, he proved from 2012, he proved that part 2 fails. Well, it fails as stated. Then a few years later, Heller, Krishna and me in 2015, we showed that 2 doesn't hold as stated, but it holds rationally. So because of this, because point 2 holds rationally, there's still a chance that the program can go through. But then Oiva, Krishna, and me in 16 showed that that part 3 is not true. So it's really the negation of part 3 that holds. So what we proved is that the map, should probably raise this board a bit. C. So on mu p equivalent k naught, the map from kr to spec C, this is an isomorphism for almost all primes p. That is an integral statement, yeah. Right. Okay.
Okay, but that could still be one.
Yes, could still be one, but if one looks carefully at the proof of one here, one can check that the primes cannot be really. There cannot be any primes here and in 3.
And in 2, you only use y equal to a point.
Let's see. Yes, exactly. In 2 here, we're using the map from A1 to a point
So
in this here.
The counter example is also for a point. It's also for a y equal to a point.
Yes, I think so. Yeah. Okay. So then instead of trying to, so since this fails, let's sort of try to prove the contrapositive. So, so let's try to outline the proof of theorem 1 that the Korras-Russell threefold is indeed A1 contractible. So outline of theorem 1. So the idea here in the beginning of the proof, all of this is due to Dubelow and Facel. Okay, so let's look at KR. Now, let's inside KR we find a line, a copy of A1, just by setting the coordinates x, c, and t to be 0. We find something that's an affine line in the variable y. On the other hand, we can look at the hypersurface cut out by setting y to be 0. So h, y, 0. Now, if one sets y to be 0 and play around with the equations for kr, one recognizes this here as an a2. This is an a2 in the variable c and t. Okay, so inside kr we find a copy of a2, and the idea now is to show that this inclusion here is an a1 weak equivalence. I mean, if so, then because A2 is clearly A1 contractible, then KR is also A1 contractible. Okay, so we have H. We look at a map into KR. And inside KR, let's take out the line L. And notice here that L, the intersection of so L here, L was supposed to be this line here. So the intersection of L and H is just the origin. So there's a pullback here where we find A2 in C and T, where we just take out 0. And of course we identify H here with A2 as we said before. Okay. So the question is really if this is an A1 weak equivalence. Now let's look at the cofibers of these maps. So here when we look at a cofiber, we look at a quotient of A2 by the function A2, then we get a smash product of P1 with itself. Okay. So let's call this diagram here for star. So the idea is, well, there's actually a sort of a five lemma in model categories saying that if you have such a commutative diagram of homotopy cofiber sequences, if the left-hand side is a weak equivalence, the right-hand side is a weak equivalence, and one of these guys here in the middle is contractible, then it follows that the map in the middle is also a weak equivalence. So, so the idea is to show that both the left-hand side and the right-hand side are A1 weak equivalences. And there's another ingredient here. So, so when we look at KR, remove this line, we can look at the projection in the x and t variables down to A2 in x and t, taking out 0. And this map here turns out to be an A1 weak equivalence, but not for trivial reasons. This is really a very delicate point in the paper of Duboulot and Facel to show that this here is an A1 weak equivalence. Okay, so we're in the situation where the sources and the targets of the maps on the left and the right-hand sides can really be identified. So to see that the map on the right-hand side is a A1 weak equivalence, this is an explicit calculation with the equations for KR and an application of the purity theorem. So let's just note that.
So excuse me, why this is subtle at this A1 equivalence? Fibers are all A1, right?
No. If you look at the principal open where in here where x is non-zero, then the fibers are A1. But apart from that, it's not a sort of a locally trivial A1 fiber bundle. I mean, as it turns out, this map here factors through some algebraic space that smooths over this punctured affine plane. So it's really a delicate point. Okay. So the right-hand side, so if you look at this quotient, then by the Thom isomorphism, we have an A1 weak equivalence with the Thom space of the normal bundle of L inside KR. And this turns out to be generated by the global sections C and T. So this is same as the Thom space of the trivial rank 2 bundle over A1 in the variable y, generated by C and T. So this here we can identify with A1 y plus smash P1 slash P1, and the map on the right hand side is just induced by the map from, well, the rational point 0 on A1. Okay? So clearly that map on the right hand side will be an A1 weak equivalence. Now on the left hand side, so because of this identification of the complement of L and KR with A2 taken out 0, we use the fact that if you have a map F from AN taken out 0 to itself, then this is an A1 weak equivalence. That's if and only if the induced map F up a star in cohomology, say in Hn minus 1 cohomology of AN, taking out 0 coefficients in the Milnor-Witt K-theory sheaf in degree n, this here is an isomorphism. I mean, this is a corollary of the fact that A1 homotopy classes of an minus 0 to itself identifies with this cohomology group here on the right-hand side. Okay, so what we do is we apply. So now applying, let's see, H star. So sheaf cohomology with coefficients in the second Milnor-Witt K-theory sheaf to this diagram, then a diagram chase reveals that it suffices to show the vanishing of some group, namely H2 Kr, coefficients in K to Milnor-Witt. Okay. So to attack this problem, this vanishing here, we will use the projective bundle theorem due to Facel. And the idea now is to sort of take this group that we're interested in and smash with more and more copies of P1. So in some sense, what we're doing in that operation is just to stabilize the whole problem. Okay. So we have projective bundle theorem saying that Hi, well, let's just write it out for Kr. Coefficients in this Milnor-Witt K-theory sheaf. So this is an isomorphism due to Facel. Identifying this with H, let's see, I plus n of Kr. Now we added an extra base point. We smash with P1 n times, and we're taking coefficients now in K MW of J plus n. Okay, so we want to combine this here with a split cofiber sequence of this form, namely P1 smashed with itself n times, mapping to Kr, plus smashed with P1 n times. And here, I just want to take Kr smashed with P1 n times, and you may ask what we mean by this here. Well, Kr has a canonical rational point, namely the origin. Okay, so this sort of brings us to the stable situation. So let me phrase theorem 2. So this is due to Oiva, Krishna, and me, and it says that Kr smash P1 smashed with itself n times. This here is A1 contractible for n sufficiently large. Okay. So of course theorem 1 says that we can take n to be 0, right? But in the way we prove this theorem is we have no idea what n is. Okay, so given the input of theorem 2, what we learn is that Hi, Kr, now coefficients in H Milnor-Witt J, this here will be isomorphic just if n is large enough to I plus n of Kr, of P1 smashed itself n times, coefficients in this Milnor-Witt sheaf in degree j plus n. And this here, this is known to vanish for I positive. Right? So this implies, well, this implies theorem 1. Right? I mean, we're only interested in the case where I and j equals 2. Okay. So we're left with proving theorem 2. And proving the proof of theorem 2 really works in the stable motivic homotopy category, where we use techniques such as the slice filtration to deduce this result here. Okay, so so theorem 2, well, this follows by showing, so this is all stably, so in the stable motivic homotopy category, that the suspension spectrum of Kr with respect to the origin is contractible. So let me write A1 just to emphasize that we're doing this motivically. Okay. And because the proof is done in this way, we really have no chance of nailing down a priori what this n in this theorem 2 is. It's really just an existence theorem. So this statement here that the suspension spectrum is contractible follows from two facts. Namely that the suspension spectrum this is, on one hand, it is MC acyclic. So MC here is motivic homology. So it's MC acyclic. So that just means that it dies after smashing with MC. So MC smashed with the suspension spectrum. This is contractible. And secondly, it's MC local. So MC local means the following, that when we look at maps, say in the stable homotopy category over the complex numbers, from some E into the suspension spectrum, Kr0, well, this here is 0 for every MC acyclic E. Okay, so acyclic and local is just in the sense of Balsville in the classical situation. So one should notice here that since MC is a ring spectrum, all the modules over MC are actually MC local. Okay. Okay, so in order to prove this, there's a fair amount of explicit calculations that comes in. I mean, really with these equations that we wrote up in the beginning, So in order to prove 1, we show that for x, say it's a smooth affine complex variety. If you look at the map, well, we claim there's an isomorphism from the motivic homology of this x into the motivic homology of x cross kr. Okay, so this is really an explicit calculation. And it follows from from using localization sequences. So this is telling us that Kr in the isomotivic homology, Kr is really contractible, right? I mean, this is really what it's saying. And in addition, to prove 1, we use that. Plus, we use that suspensions of the suspension spectra of x plus for x affine. These generate. So taken together, this generates SH of C. And there's also a duality argument coming in here, namely that the suspension spectrum of Kr is dualizable, or strongly dualizable. Okay, so there is a bit to do there. Yeah, I mean, suspending in all sorts of directions. I mean, yeah, so, okay. If you like, let me put in D. Okay, so that step is something that's very specific to Kr. But step 2, this holds more generally. So step 2, this holds for any x in SMC and rational point x on x. So the proof of that really uses the full strength of the slice filtration. So this follows from the slice filtration from computing the slice filtration for suspension spectra, say. Okay. And the fact that what it really comes down to in the end is that all the slices of suspension spectra are MC local. But that follows because all the slices are modules over the zero slice of the sphere spectrum, which we know are MC. I mean, the zero slice of the sphere spectrum is motivic homology. So that's another basic fact that goes into the proof of 2. So let me skip further details because I think in the interest of time I should really, I would like to add a postscript to this story. In some sense, it's quite frustrating for a person doing motivic homotopy theory that we cannot distinguish between the Korras-Russell threefold and A3, because the Markov-Limonov invariant is strong enough to distinguish the two. But I mean, even with all the fancy machinery we have in motivic homotopy theory at at this time, it's not possible to distinguish them. So there's something sort of, one might feel that there's something missing in this theory. And to get some feeling for what is missing, I think we should look to topology. So in topology, there's this beautiful characterization of Euclidean spaces. This is a big theorem. So R, n greater or equal to 3, this is the unique open contractible n manifold that's simply connected at infinity. So simply connected at infinity has to do with proper homotopy theory. It basically means that every loop that's sort of far away from a small subspace of Rn here can be contracted. That's intuitively what that means. So what I want is the sort of a theory where it makes sense to talk about some motivic homotopy groups at infinity. So I want a version of proper, say, proper A1 homotopy theory. So let me just go ahead and state something that's really science fiction at the moment, but maybe one day. So something like an A1 Poincare conjecture. So suppose we have something. Suppose X is an SMF, so it's affine, say complex, and it's A1 contractible. So if, let's say, if X is properly A1, weakly equivalent to some affine space AN, well then X is really AN. Then X is isomorphic to AN as a variety. So that's a sort of a possibility of an A1 Poincare conjecture. At the moment it's sort of science fiction because we don't really know what properly A1 weakly equivalent should mean. Okay? But the real test case here, and this it's sort of similar to the story of the Whitehead manifold. When Whitehead gave a wrong proof of the Poincare conjecture in 1931, the mistake was claiming that every open contractible free manifold is R3. But there's a counterexample to that, and the counterexample is the so-called Whitehead manifold. And in some sense, the Whitehead manifold is analogous, or the Koros-Russell freefold is really analogous to the Whitehead manifold. So the real test case here is to develop some proper A1 homotopy theory that can distinguish the Koros-Russell freefold from A3. Okay. I could say that I have a beautiful proof, but my time is up, so I can't tell you something. Thank you. Yes, but we're in characteristic 0.
This one is true.
Yes,
Still realize more.
yes.
Do we know for KR threefold, do we know the weaker version of varieties cancellation, namely KR times an affine space, not affine lines isomorphic to another affine space?
I don't know that expression for KR, but there are counterexamples in general, right?
So to this weaker version too?
Yes, even to the weaker version, even for surfaces. The so-called Danilevsky surfaces are counterexamples to that type of cancellation problem.
Other question?
So do we know any non-trivial vector bundle defined already is KR three-folded?
If you know,
Are any the non-trivial vector bundle defined?
no, they're all trivial. Sorry, yeah.
There are no more questions. Let's thank the speaker again.